So, in this lecture, we'll start new topic, that is solution of nonlinear equation. So, one of the most frequently accuracy, one of the most frequently occurring problem in scientific work is to find the root of an equation of the form f of x equal to 0. So, f(x) equal to 0, it is a nonlinear equation. Nonlinear equation could be of two kinds of. First is polynomial equation and second is transcendental equation. Polynomial equation means what? Like the form xn plus xn minus 1 and so on. Let us take an example, x cube plus 3x square plus 2x plus 1 equal to 0. And transcendental equation, that means the equation involving functions x plus sin x equal to 0, log x plus tan x equal to 0, e raised to power x plus sin x plus x equal to 0. So the equation that is involving functions, those are called transcendental equations. So the solution of the nonlinear equation means what? We have to find solution of the polynomial equation or the transcendental equation. So transcendental equation may have infinitely many roots or no real roots. So in that case, we are not having any simple technique so that we can find the solutions. For that, we are going to discuss numerical solution. So in this lecture, we will introduce some elementary iterative methods for finding the solution of nonlinear equations. Or zero of the nonlinear equation. First method that we'll discuss, that is what? Bisection method. In this particular chapter, we will discuss different methods. First is bisection method. Second is fixed point method. Third, Newton's method. Fourth is Bisection method. All these methods will be used to find the solution of nonlinear equations. So the very first method that we are going to discuss here, that is bisection method. It is used to find solution of the nonlinear equation. Okay. So this method, it is based on intermediate value theorem. This theorem is also we can call in short IVT theorem. Okay. IVT theorem. What is IVT theorem? Let's write the statement of the theorem. IVT theorem or intermediate value theorem. It is said that suppose I should write in a from intermediate value theorem. Okay. Suppose f is a continuous function. F is a continuous function defined on the interval AB with f of a and f of b are of opposite sign then there exists at least one or odd number of roots in the interval AB. That means what? F is some continuous function that is defined inside the interval AB. So inside the interval AB, function is continuous. And f of a, f of b are of opposite sign. Okay, if f of a is plus, then f of b is negative. Then there exists at least one or odd number of roots in this interval f of a, inside the interval AB. Let us explain it with the help of graph. Suppose this is x-axis, y-axis, and the function is fx. And the function is, suppose this function is continuous between the interval a and b. So this is the point A, and this is your point A, and this is the point B. In this interval AB, function fx is continuous. And f of a, this is what? Positive. F of b, this is f of b, and it is f of a. F of b is what? That is negative. So f of a and f of b are of opposite sign. Then if f of a, f of b are of opposite sign and the function fx is continuous between a and b, then it will certainly cross x-axis at least once inside the interval AB. So this is what? This is the root where the function fx crossing the x-axis. Okay, so this is the intermediate value theorem. Whenever function is continuous inside the interval AB and f of a, f of b, they are of opposite sign, then the function fx cuts x-axis at least once inside the interval AB. So this is the example we have shown graphically. That is the best example of intermediate value theorem. The function is like that. And suppose this is the point A and this is the point B. This is your A point and this is the point B. Between A and B, this function fx is continuous. Okay. And at this point, this is the function value f of b. That is what? Negative. Here the function value f of a, it is positive. And the function is continuous. It is crossing x-axis 3 times inside the interval AB. Okay, so the root of this function is what? Suppose alpha 1, alpha 2, alpha 3. These are the root of the function f of x between a and c. Okay, if this is possible only whenever f of a and f of b are of opposite sign. One is plus and another is negative. Or we can say their multiplication is what? That is less than 0. What will happen whenever we are having f of a, f of b greater than 0? What will happen? What will happen? Okay. Whenever f of a, f of b is greater than 0, let's draw it. Okay. And we are having function like that. And here, this is the point, suppose a, and this is the point b. Here, f of a is positive, f of b is greater than 0. Okay, multiplication of f of a and f of b is greater than 0. Then it will cross x-axis even number of times. Okay, so whenever f of a, f of b is greater than 0, there exists either no root or even number of roots in the interval AB. Condition is what? That f of x should be continuous. Okay, no root. Let's take an example of no root. If this is x-axis, y-axis, if the function is like that. Here, this is the point A, this is the point B. F of A, f of b, f of a, f of b greater than 0. But it is not crossing x-axis anywhere inside the interval AB. So just keep in mind, whenever f of a, f of b is less than 0, then there exists either 1 or odd number of roots inside the interval. If f of a, f of b is greater than 0, then there exists no root or even number of roots inside the interval AB. So intermediate value theorem is basically for the case whenever f of a, f of b is less than 0. Okay, so let's explain bisection method. Bisection method is the simplest iterative method for finding the real root of an equation f of x equal to 0. It is based on repeated application of intermediate value theorem. We need to initial guess a and b such that f of a, f of b is less than 0 in multiplication, and fx must be continuous inside the interval AB. Then AB must contain the root. Okay, let us explain this method graphically, then we'll explain it numerically. So what we do first? Continue. Okay. Let us suppose this is the function. Let us suppose there is a function fx, and this is the point A, and this is the point B. Okay. These points A and B we can compute either by guess or by intermediate value theorem. Okay, so in bisection method, first we required function. This function should be continuous inside the interval AB, and then in bisection method, what we are doing, we are trying to find out the root of the function. Okay, fx equal to 0. So what we do first, we'll divide this interval AB into half point. Like first what we do, we'll find out the midpoint of the interval AB. Let us suppose the midpoint of the interval is what? That's C1. Okay, this C1 is what? A plus B upon 2. Okay, so what we do, first we'll compute. So first step of the bisection method is what? Compute midpoint of the interval AB. Okay, so this is the midpoint C1, and what we'll do, check here, we'll check that f of C1 is what? This point. So function value at the C1 will be what? This, f of C1. Okay, now we'll check f of A into f of C1 is less than 0, or f of C1 into f of B is less than 0. Okay, what we do first, we'll find out the interval AB, and then we'll check function value at C1. C1 is what? That is the midpoint of the interval AB, and we'll check either f of A, f of C1 is less than 0, or f of C1, f of B is less than 0. Okay, at least one of the condition will be there. If it is equal to 0, then C1 is the root. If C1 is not equal to f of A, f of C1 is less than 0, that means root is lying at least in one of the intervals, either in A1 C1 or C1 B1. So if you see graphically here, C1 is the midpoint of the interval AB, and root is lying between the interval A and C1, because f of A is what? That is, f of A is negative, f of C1 is positive. So the f of A, this implies here that f of A, f of C1 is less than 0. That means root is lying inside the interval A, C1. Okay, so what we do, first we'll write A1 as A and C1 as B, because this is the next interval in which the root is lying. So A1 will take as A and B1 take as C1. Okay, so the root is lying inside the interval A1, B1. So now our interval reduced to, this is A1, B1. From AB to the interval reduced to A1, B1. And length of this interval, let us suppose the interval is what? That is I1. Okay, length of this interval, length of I1 is what? That is B1 minus A1. Okay, B1 minus A1, or B1 minus A1 is what? That is half of the length of AB. So we can say B minus A upon 2. We can say 2 is to 1. Now we'll again apply intermediate value theorem. What we do, we'll bisect the interval AC again. Now bisect the step 2. Step 2. Bisect the interval A1, B1. So what you are getting? You are getting second point. Midpoint of A1, B1 is what? C2. Let us suppose it is C2. Then A1 plus B1 upon 2. Okay. So let us suppose C2 is somewhere here. This is your C2. Okay. So C2 is what? That is negative. Function at C2 is what? That is negative. So either f of A, f of C2 is less than 0, or f of C2, f of B1 is less than 0, because C1 is nothing, it is B1. We have replaced it here. Okay, so either f of a, f of c2 is less than 0, or f of c2, f of b1 is less than 0. From here, from the graph, it is very clear that root is lying from the graph. From the graph, it is clear root is lying in the interval c2 b1. So let us give the name to this new interval a2 as c2 and b2 as b1. Okay, so the new interval is what? a2 b2. Let us suppose this interval is what? I2, and length of I2 is what? That is b2 minus a2, and it is half of the b1 minus a1 upon 2, and b1 minus a1 is what? That is the b minus a upon 2. Length of the interval b1 minus a1 is, length of the interval a1 b1 is what? That is b minus a upon 2. We can write it like that. So we can say length of a2 length of I2 is what? That is b minus a upon 2 is what. Continue this process. We'll get an interval in, and length of the interval is what? bn minus an, and it is equivalent to b minus a upon 2 raised to power n. Okay, continue this process. We are getting in. Okay, and length of in is what? Length of in is what of bn minus an, that is b minus a upon 2 raised to power n. As n is tending to infinity, as n is tending to infinity, then limit n is tending to infinity in equal to limit bn minus an is coming out to be infinity. It is equal to limit n is tending to infinity b minus a upon 2n. We will continue this process till we are getting bn equal to an. That means what? We are moving toward a single point. So the interval what we are doing here, we are dividing the interval AB. We have divided the interval AB into half of that interval, and we are continuing this process. Ultimately, we are getting very, very small interval that is containing a single point. That means we are getting bn equal to an, or it is moving toward the root alpha. Okay, so length of the interval, that this implies that limit of in is equal to 0 from here and is tending to infinity. 2 raised to power n is in the denominator. So we are getting limit of in is equal to 0. So a very, very small interval, very, very small interval containing a single point. Okay, so this is the bisection method. So I think it should be clear. So first we were having an interval AB. We have divided this interval into two equal parts. We got the midpoint C1. At C1, we'll check where the intermediate value theorem is satisfied. Inside the interval A1, A, C1, the intermediate value theorem is satisfied. So we'll take this interval where the root is lying, and then we'll divide this interval A1, A, C1 into two equal intervals, and we'll find out in which interval the root is lying, and we'll continue the process. Ultimately, we are getting a very, very small interval that will contain the root. Okay, so this is the bisection method. Okay, so when to stop? Here, this is the theoretical result. If we see we are doing it numerically, then when to stop. Just keep in mind we started with the interval I1 containing I2, containing I3, and so on. We are getting this thing like that, and so on. Okay. So when to stop? It depends on accuracy, how much accuracy is required in our question. So accuracy up to n digits. Stop when we get accuracy up to n digits. Okay, up to n digits. Up to n decimal digits. N decimal digits. Let us take in decimal digits or decimal places, whatever you want. Okay, stop when accuracy up to n decimal digits is okay. Means suppose you are suppose n equal to 3 we want to take. So what we do, will compute in this case we are getting sequence like midpoint sequence. First we got here C1 and then C2. Here we are getting sequence like C1, C2, C3, Cn. Okay, we are getting sequence of the midpoint C1, or we can say we are getting sequence Cn. Okay, so C1, C2, C3, Cn are what? These are the midpoint of the interval I1, I2, I4. Sequence of midpoint. Okay, so whenever the consecutive value of the sequence, suppose Cn minus 1 is less than 0.0001, then we'll say 3-digit accuracy we achieve. That means what? If C1, suppose Cn is equal to 0.213, that means 3-digit of Cn are same. That is suppose 4, and Cn minus 1 is what? 0.213, whatever the fourth value. I will suppose 5. Okay, then Cn minus 1 will be what? It will be 0.0001. Okay, or we are taking here any value. So this is what? It is less than epsilon, or we can say it is less than 10 raised to power minus 3, less than or equal to. Okay. So we can say we got desired accuracy. So up to if we required accuracy up to n decimal places, so at least n decimal places of the consecutive sequence should be same. Okay. So let's do one example, then it will be more clear. This is the bisection method. So this is the one more thing I want to explain here is stopping criteria. There are 3 kinds of stopping criteria. Whenever we are getting sequence of the solutions, like sequence of the approximate solution. Stopping criteria. One is absolute error. That means whenever we are getting sequence of the approximate solution, when to stop. Whenever absolute error between the consecutive value of the sequence is less than epsilon. This is approximate error. Second is relative error, xn minus 1 upon mod xn is less than epsilon. Third is what? F of xn is less than epsilon, where epsilon is solvent. Epsilon is solvent. So in the first case, there is a problem. Sometimes the difference xn minus 1 may converge to 0 while the sequence itself diverging. Okay. Sometimes, like, these are the three stopping criteria that will follow in throughout this chapter. One is absolute error is less than epsilon, relative error is less than epsilon, and the function value at xn is less than epsilon. So there is one drawback of the first criteria. What is that drawback? Sometimes we may get differences near to 0 or difference is less than epsilon. But it may be possible that sequence xn, it is not converging toward the root, it is diverging. Because xn or xn minus 1 could be a very, very large number. But their difference may be very, very small. So if we are checking only this thing, then we can say, oh, it is converging toward the root. But it is not always the case. Okay. About the third criteria, f of xn may be close to 0 while xn differ significantly from the root alpha. Okay, so first criteria, like these are the three criteria. First criteria may create problem whenever the sequence is diverging. Okay, and xn and xn minus 1 are very close to each other, but their difference may be very small. So it may create confusion. In the third case, function value at some point is coming out to be 0 or it is less than epsilon, but it may not be the root of the function or the equation. So whenever we are using these stopping criteria, we should be very, very careful about the sequence also. Okay, so out of these three criteria, in general, second criteria give better results. Best, we can say. Okay. So these are the three stopping criteria we'll use throughout this chapter. Next is bisection method. Do some example. Let's do one example. Use bisection method to find the solution accurate to within 10 raised to power minus 1 for the equation x minus 2 raised to power minus x equal to 0. So what we have to do, we have to apply bisection method to find the solution accurate to within 10 raised to power minus 1. That means function is given to you here x minus 2 raised to power minus x equal to 0, and the tolerance is given to you as 10 raised to power minus 1. Okay. Now, first of all, what we require to apply bisection method? Interval in which the root is lying. So what we do, it is based on either guess or we'll apply some hit and trial method. So if you see this equation, x minus 2 raised to power minus x, we'll check function value in positive direction or negative direction. It is an equation that is containing infinitely many roots. So we'll just check f of 0. What is f of 0 is coming out to be 0 minus 2 raised to power minus b. It is coming out to be negative value. We'll take f of 1. It is coming out to be 1 raised to power 2 raised to power minus 1. This is 1 by 2. It is the positive value. So in this example, we got in the starting interval 0 and 1 in which the root is lying, because since f of 0, f of 1 is what? That is minus 1 into plus 1 by 2, it is negative. Less than 0, so 0, 1 contains at least one root inside the interval 0 to 1. Okay. So let us take a equal to 0, b equal to 1. So let's explain it with the help of table. And we are finding what? a1, a2, a3, an. That's why we are writing an, bn, cn, f of n, function value, f of cn. Okay, n equal to 0. So what we got in the starting? 0, a0, b, and v value in the starting, it is what? 1. Midpoint of this, that means c1. That is what? 0 plus 1 upon 2, that is 0.5. So we are getting 0.5, midpoint of a and b, that is 0.5. And the function value at a0, function value at 0 we have already computed, that is minus 1. And function value at 0.5. So function value at 0.5 is what? F of 0.5 is coming out to be 0.5 minus 2 raised to power minus 0.5. So this value is coming out to be minus 0.2071. So minus 0.2071. Okay. Now we'll check f of an multiplication f of cn. And then we'll find out cn minus cn minus 1. Okay. So f of an into cn, negative, negative, that is positive value. F of an into f of cn. And cn minus 1, so we are having nothing in this starting, so we'll keep it as it is. Now, at the first equation, since f of an, f of cn, it is coming out to be positive. So if we see graphically, if we call, if the function is something like that, a is 0, function value at 0 is what? That is negative, and at 1 is what? It is positive. So function is something like that. Okay, so this is the value, this is your 0, that is your a, this is your b equal to 1, and function is somewhere here, root of the function is somewhere here. So f of 0 is what? That is negative, we are getting here. F of 1 is what? That is 1 by 2, f of 0. Okay, so we are getting midpoint. Midpoint is what? Somewhere here, suppose 0.5. 0.5. So it should be somewhere here, 0.5, because function value at 0.5 is coming out to be negative. This is the value, 0.2071, negative value. So that's why so f of a is negative, f of a is negative, f of c is negative, c1 is negative, we can say. So in this interval, no root is lying, root is lying inside this interval. Okay, so what we do here, so c1 is your a, so c1 will be your a, and b is your b1. Okay, so now a1 is your c, that is 0.5, and b1 is as it is at this position. Now midpoint of 0.5 and 1, it is 0.75. 0.5 plus 1 upon 2, it is 0.75, and the function value at an, 0.5, we have already computed this value, that is negative, minus 0.2071. and new Cn is what? That is 0.75, that is C1, and the function value at 0.75 is what? That is 0.1554. Okay, and this is function value at A is negative, function value at C is positive, so the multiplication is what? That is negative. Okay, and C1 minus C0, 0.75 minus 0.5, it is coming out to be 0.25. This value is negative, but we are taking mod, so that's why we are getting this value is greater than 10 raised to power minus 1. Okay, so we'll continue this process, second iteration. Now, since this value is what? Negative. Negative, that means the root is lying between A and C. So next, A will be what? That is your A as it is, 0.5, and B will be what? That is your midpoint, that is 0.75. Okay, and the midpoint of 0.5 and 0.75, it will be 0.625, and function value at 0.5, that is same, 0.2071, and function value at Cn, 0.625, it's 0. minus 0.0234. Multiplication of these values are what? Positive. Positive, that means what? Root is not lying inside AC, root is lying between C and B. So C will be what? That is your new A. So C will be your new A, that's why 0.625, this is your A, and B will remain as it is, 0.75. And the value of C, midpoint of this, it is coming out to be 0.6875. Okay, and function value at 0.625, it is minus 0.23, negative value 0.0234, and function value at 0.6875, its value is what? 0.0666. Multiplication is what? Negative. Okay, just take the value between the difference between C and Cn minus 1. So the value is what? 0.75 minus 0.625. This value is coming out to be 0.125. That is again less than epsilon. Epsilon is what? That is your 10 to the power minus 1. Okay. Now, this value is coming out to be 0.625. Okay. So this value will be what? 0.625. It is again 0.0625. Okay. So we can say this value is what? This value is less than epsilon. So we can say this condition satisfies here, since Cn minus 1 mid value or the sequence of the midpoint, it is less than epsilon, so we can stop here. Okay. So what would be the root of this equation? With this stopping criteria, the midpoint of the interval 0.625 and 0.75. So 0.6875 is the root of the equation with the stopping criteria 10 to the power minus 1. So 0.6875 is the root of the equation fx equal to x minus 4 raised to the power minus x. Okay. If the stopping criteria change, then the number of iteration will increase. Okay. It depends how much desired accuracy is required in the question. Okay. So if you see in this question, C2 and C3 value, C2 and C3, they are same at the one up to the one digit, like 0.6 and 0.6. They are same, and the second digit they are differ. That's why in this question it is required the desired accuracy of one digit. That's why the difference is what? That is less than 10 to the power minus. Okay. So this is the bisection method. In some books it may be given, it is also given, like suppose the interval is what? 0. Like after this we are getting the another interval. Suppose A1 is what? A3 is what? 0.625 and B3 is 0.75. It is containing the midpoint at 0.6675. So in some of the books they follow like find the fourth iteration. That fourth iteration will be what? 0.625 and 0.6875, and the midpoint of this 0.65625. They take the mid value of the next interval as the root of the equation. So according to Warden and Fair, this is the 0.6875 is the root of the equation. X minus 2 is 4 minus 6. That is correct to 1 decimal place. Okay, thank you. So we are in the next class we will discuss about the number of iterations required to get the desired accuracy of 10 to the power minus n, and we will discuss the convergence criteria of the bisection.